like that's interesting to me with the recent earthquake patterns, and I think you guys will find some interest in this as well, and it'll probably set the scene for some future discussions. And when things happen, we can refer back to this summary. I've tried to make it a summary of the Southwest Rift in Kauai, and so I'm going to show you guys on this map, USGS map of lava flows from Kilauea since 1790. The summit's right in here. The Southeast Rift is this whole thing over here, and all these colored blobs or lava flows coming off of the rift zone. So you can see a lot of lava flows off of the East Rift Zone, and that's what we talk about most of the time, is that or the summit. So we're not going to do that today. We're going to focus instead on this other area. This is the Southwest Rift over here, right? And there's an area in between the two right through there, and that's the Koaʻe Fault Zone right through there. And we'll see better images of this so far. But I wanted to first just point out this distribution of lava flows on the volcano. You see, obviously a lot in the summit, which with the caldera and things filling and layering over themselves in the depression, you don't see quite as much variation as you do on the East Rift, but these are the more active areas. The Southwest Rift does have quite a few lava flows on it as well, but there's a lot less that's known on them than we do for the Southeast Rift. So I'll show you guys this. This is a clip from a paper by Dvorak and Zurison in 1993, and this is looking at the volumes of magma in the volcano. So it looks a little tricky. Let me break it down for you guys. So first, focus on this. This is the key up here, this upper panel, right? This is the source of magma into the volcano from below. Here's the summit magma reservoir, of which some amount erupts onto the surface at the summit. Some goes into the East Rift Zone, can erupt in the upper Rift Zone, middle East Rift Zone, or the lower East Rift Zone. Or it can go to the Southwest Rift Zone and erupt out of the Southwest Rift Zone. So what they're showing here is of 100% of magma that comes into this volcano from below, and this is a period of time that spans from 1960 to 1989. So this does include that first beginning of the pool era, and it would be skewed even further today, since we've had a lot more East Rift Zone activity with nothing else anywhere else in much of that time. So this is a little bit dated, but it gives you some idea of that distribution. 100% of magma comes in. Of that, about the same amount is going all the way through to the rift zone. In this case, it's 106%. The reason why is because you actually have a deflation of the summit long term during this era. The summit's losing magma in the long term. It's feeding the rift zone. It's feeding some eruptions at the summit. But most of the magma coming into the volcano is going through to the rift zone, right? Where of what's coming in, 38% is being retained underground. And you have coming out of the Middle East Rift Zone by pool area 47% at the time. Now it'd be even higher. Coming out of the Lower East Rift Zone, only 5% of the volume. This is pre-2018. This would be higher. And out of this Upper Rift Zone, 16%. This would be lower. And so, but that's more or less the proportions historically, right? So you can see that, roughly speaking, of what goes into the Rift Zone, maybe a third of it is being kept underground, and the rest is finding its way out somewhere. That's one interesting thing to take from this. But compare that to the Southwest Rift, right, where only 10% of the magma is going into that area in the first place. Of that 9% is being kept underground, and only 1% makes the surface in the Southwest Rift. This number would be lower now because of everything else going up on this side, right? So this is what I want to point out, is really this pattern of the Southwest Rift, where it doesn't get nearly as much magma, maybe a 1/10 ratio, 1 to 10 ratio between the Southwest Rift and the East Rift. And of that amount, only 10% of it comes to the surface. So a lot of this is happening underground, adjustments underground. It's just one big difference to kind of start off with what's different between the Southwest and the Southeast. That explains the patterns we just saw on the map. So focusing on the Southwest Rift only, there are a few historically documented eruptions, and only a few. These 5 right here. 1823, which was William Ellis. Didn't actually see it happen, but he did hike across on the way up to Kilauea, the still cooling lava flow of 1823. We have a lot of other flows here between 1790 and 1815. 1815 and 1823. All these are things that are fairly recent science additions to our catalog, and there are no historical records of people witnessing these that we have linked to these as of yet, at least, right? Maybe if you go back and look closer, and surely someone is, you might find something like that, but right now these are not anything we have any other information on besides the fact that they're there, and the carbon dating ages came back around then, right? We have to jump to 1868, which was a very small eruption. Just one little pad right in there, about that big. And then to 1919 and 1920, this was Mauna Iki, the largest southwest rift zone eruption in, well, I guess it was about a century ago now. I was going to say in the last century, but not quite anymore. A little over a century. And then we have a big gap before 1971, which starts up at the summit and propagates its way down a little bit here, and then down across 1919. And 1974 was a little offset to the south, but that was the most recent southwest rift zone flow that was entirely outside of the caldera. And there are a lot of similar structures within the caldera, near the caldera, that have similar trends, but we're going to call all that caldera stuff and leave it apart from our discussion today. And so my goal isn't to describe how every eruption actually happened necessarily, like the full eruption, give you a recount of everything. That would take way too long. I'm going to focus instead on the dynamics of how we saw these eruptions actually happen, to understand how they might happen in the future, what might be necessary to cause this event, this pattern to reemerge. So let's go there and see where that takes us. Oh, wrong way. All right, so 1823 in the Southwest Rift, and I'm going to shrink this down a little bit. Over here, okay. 1823 in a Southwest Rift. Kilauea is the lava flow that William Ellis, the first Western missionary to the island of Hawaii, described. And he actually drew this sketch right here. And in this sketch, which is this map up here on the right from Hazlitt and Henman, you actually see that there is this inner depression, right, within that outer depression further out. I might need a different color. Oh, let's change my color here. So an inner depression within that outer depression over there, yeah? So in the image here, you see that as this is the black ledge right through here. And this was interpreted as being essentially that high point of lava before it had just drained to go somewhere. And the conclusion was then, and we have no reason to change that now, is that this is what fed that eruption down on a Southwest Rift at Kilauea. So what we're seeing essentially is a pattern of there was magma, there was a lava within the lake at the summit, at very high elevation, as far, filling it to its highest point to that level, right? That's what this big ledge is over here. And then it quickly drained down to feed something downhill, and so that's why that's associated. This is a Google Earth satellite view of this eruption site. This is this big black feature all through here. What you might be able to tell is that there's this crack. This is the Great Crack, the world famous, visible from the space shuttle, Great Crack of Kilauea. That's the surface manifestation of the extension of the Southwest Rift Zone. It runs all the way like that. Right? It's kind of off in the middle of nowhere. It's not the easiest to find and get to, but it's super long, and you actually, it's a very interesting feature there. And it appears like this lava flow came out of this crack. Right? You can kind of see that the pattern really comes out of that. It's interesting. The crack is there now, and the crack likely didn't stay a crack during the eruption, but since then there have been a lot of earthquakes. In particular, there's a big earthquake in 1868, just over that way, that we know caused eruption in 1868, as well as likely opened this crack a little more as well. So this is one of this is the only one we have an example of in historic time that actually make it to the ocean in the Southwest Rift. So that's pretty rare, and but that shows you that essentially you can have a full lava lake at the summit, and it drains out through a crack all the way down to sea level. This is not. It's not too unlike what we saw in Leilani in 2018, where high lava lake at the summit, a big crack, and it drains down the crack. The difference is the structure underground of this rift. This crack is not nearly as deep as the East Rift Zone conduit, and I'll show you guys that as well. So you maybe didn't have quite as much space to feed quite as much lava maybe didn't quite induce that same level of summit collapse that we saw in 2018, and that's why it was different, perhaps. But you would imagine that that's something to consider for the Southwest Rift as well. And maybe the underlying structure prevents it from doing that, and we'll talk about that here shortly. This is the 1868 estimated area of ground movement and rupture, right? So this is Mauna Loa up here, and Kilauea is down over here, and Mauna Kea over here. You can see that they believe that this entire southeast flank of Mauna Loa, all the way to South Point, of which Kilauea and its east rift are part of it, that entire thing was what moved to generate what's considered a magnitude 7.9 earthquake in Waiohino here, in this area on the south flank of Mauna Loa. So you can see in red, this is the Southwest Rift Zone eruption right in here. There's really not a lot of information on it, apart from its location there. And there's also a small eruption near Kilauea Iki, near Byron's Ledge area at the summit as well. So a couple of small things. Everything got so shaken up. There's unconfirmed reports of plumes of gas and fume rising from craters on the East Rift Zone. So it's unknown, no confirmed eruption on the East Rift Zone, but certainly there was big movement and likely some collapse, maybe some steam, and maybe there would have been something glowing if there would have been enough people to look for it. But really fascinating event, 1868, right there. So moving on to 1919. This one I'll spend a little more time on because we have more information, and courtesy of Dr. Scott Rowland at UH Manoa, who presented this at After Dark in the Park. And I'm not going to go through everything once again because it's way too much, but let's talk about the initiation and the first stages of eruption, because I really want to explore this connection of the summit and its cracks going down the Southwest Rift and how that actually works, right? As part of Dr. Rowland and Duncan Moreau's paper here, they described different patterns that seem to indicate magma moving from the shallow storage area to the eruption site, also from the deep storage area to the eruption site, or sometimes the deep storage area to the shallow area to the eruption site, or or we'll see, right? But you can see that these are the elements involved. There's a shallow storage area, there's a deep storage area, and there's an eruption area, and there are pathways between all of them that bypass the other, right? That's the little I'm not sure, the triumvirate right there. Yeah. And then here's a hand-colored series of photographs at the bottom of that 1919 eruption. Okay, so, well, we'll go back and just highlight this quote here. This is the key thing. I'll read it again, but Thomas Jagger was making reports of this eruption, and he described lava could be seen flowing southwest in a crack that ran from the rim of Hawaii to the eruption site on the first phase of eruption. So that was coming up here, but let me read you guys this series of patterns here, this first two phases of pre-eruption here. November 28th, accompanied by strong seismicity, the lava lake dropped 180 meters. That's what you're seeing right through here. Two cracks in lower 120 meters of the southwest and northeast walls of the 180-meter deep pit were exposed. These cracks did not extend to the surface along the pit walls. However, a new fuming fissure opened on the caldera floor 100 meters southwest of the rim of Hawaii. That's the one that they're just describing there. So, to pause on the side here, right? They noted when the lava drained down to this lowest level, they saw those cracks in the pit down there. And they thought, oh, that's probably where the lava went, at the crack that I can see right there, right? It is concluded that lava drained into a cavity within the volcano, most likely into the fissures exposed in the walls of Hawaii. So that's what this image right here is showing. Lava lake draining into that crack, into this somewhere near the shallow storage area, right? For the next 17 days, actively fountaining lake surface arose, so they think that the deep storage came back in, pushed the shallow storage back, and refilled this, right? And it possibly could have been connected here and filling this as well, but it was blocked off at some point at the end there. Okay, so let's go to the next one. December 15th, right in here, lava could be seen flowing southwest in the crack that ran from the rim of Hawaii to the eruption site. As soon as the eruption in the caldera started, the lava lake in Hawaii began to drop. Extrusion ceased as soon as the lava level reached the elevation of the vents, reflecting a simple hydraulic link between the lava lake and the nearby vents. That's this close vent in the caldera still, that first one, right? But we're seeing a crack open near the surface. We're seeing a crack open a little bit further down, right in here, right, we're seeing cracking in this direction as the pattern we're seeing here. But the lava level kept dropping afterwards. December 16th, the lake began to rise again at an average rate of 5 meters per day over the next 5 days. And it was during this rise in lava lake level that cracks were observed propagating down the southwest rift zone. Some of these cracks contained lava, others emitted fume or steam, and others were just open fractures. In general, they formed successively in a downward direction at a propagation rate of roughly half a kilometer per day. That's roughly a quarter mile or so. By 19th of December, cracks had propagated 9.5 kilometers to the southwest. And that's what's that, roughly 6 miles-ish to the southwest there. 5.9 miles or so. So the crack is expanding, right over here in this bottom frame. The crack has moved further over. It's about to erupt out of the surface right over here, right? We've seen cracking at a very shallow level, at a deeper level, and now at an in-between level. You can see really everything is cracking. And a crack would be in that vertical plane that we're looking at it on end, like this, but it actually is a thin blade in reality there. Okay, so one last thing to note here to kind of illustrate what's possible with these kind of crack systems. Between December 24th and January 17th here, stages 2A and 2B, a lot of lava coming out during these times. The dynamics involving the extended crack system suggest both the near surface and the deeper pathways for magma movement during different stages. So you can see here that during a stage 2A, they're drawing no evidence of influx of magma into the deep storage, right? It seems like it's stable there, steady there. And shallow storage feeding on the eruption. And then at some point, after not even a week, they see the magma bypassing the shallow storage area, moving through that crack next to the shallow storage area, and then coming up and out that way. So really, this is just to show how much cracking there actually is going on there, and how magma is really moving its way into the cracks there. The cracks are a big part of it. We'll talk about how forceful this is here in a few minutes. At first, let's look at this map of the crack system in 1919. So here's a caldera up at the upper right, and end of November. And you can see December 15th here, 21st, starts working its way down, 22nd, 23rd, 24th, 25th, successively further and further away. Right? And these are the areas of cracking and fissures of that eruption. And here is eruption map. Right? So there is lava that came out. It's this lighter colored gray right in here. That's what you're seeing here. Is a 1919, 1920 lava flow over here. And then this other one is a 71 over top of it over here. Right? So that's 1919. 71, I just showed you guys where that is. Right? It's in relation. Right through there, that longer crack right through there, below Cone Peak. Right? So there it is once again. And also on this particular map is shown vectors of horizontal displacement. So you can see that there's actually, the ground is moving away from this fissure in both directions. And here's where we can talk about whether this was a forceful injection or something more passive, because if we're seeing the sides get pushed away that much, then you're likely having magma injecting into there. So you might have some, you might be taking advantage of the crack system that's there to start off, to start wedging the magma or lava in there. But at some point, the magma is actually injecting itself in there with force, because likely it's so close to the summit area. The summit area builds a lot of pressure, and when the pressure can work its way in the crack, you're going to actually have forceful injection by pressure into these cracks, and you can have crack systems and injection together, which is a little different than a Kauai we'll talk about in a little bit here. So 74 is the last one on the southwest rift before we turn to Kauai, and you can see here's a 71, here's a 74. It was outside the caldera. There's other 74 eruptions, and here they are in the caldera. We'll leave those for a different day. But the 74 eruption from fissures A through I down in here, sent flow down that reached down to not quite 2,000 feet elevation, having started up above 3,500 or so. So 74 eruption of Southwest Rift. So I've highlighted out from a paper by Wendell Duffield here some of the important things are the patterns in the Southwest Rift. And maybe I'll focus first on the image here at the bottom, right? You guys have been shown this before. We've shown you this before. Cross-section of the volcano, that lower chamber right down in here, upper chamber right through here. Our East Rift Zone is right through here. Right. Our Southwest Rift Zone has got a funny thing here. The volcanic Southwest Rift Zone, structural rift is shallower, between 1 and 2 kilometers depth. And then what's called a seismic Southwest Rift is closer to 3 kilometers depth. And it's separate, right? It's detached from that shallower structure. And to really see this well, you have to look on this map view over here. And so here you see that summit caldera area, and you see the volcanic Southwest Rift is further north and off and shallower, and then further south and deeper is a seismic Southwest Rift connected to the South Caldera deeper magma chamber, right? As we imagine that the East Rift likely also is to some degree as well, right? Possibly with shallower connections into it as well. So that's the pattern there. The first thing to notice there is this difference between the two, right? So he notes here that the East Rift essentially has that the deep core and the shallow rift, one on top of the other. And so that deeper fluid core can act as a transport region, and it could also feed eruptions from deeper that come straight up from that 3 kilometers depth all the way up to the surface in that area. That's hard to do in a Southwest Rift because at 3 kilometers depth, you're not in the same spot as you would be in the shallower part of the edifice there, right? So that's the interesting thing there, how those are actually detached, right? So the East Rift, you have that deep rift and a shallow rift stacked, and in the Southwest Rift, they're actually torqued apart. They're torqued apart, right? The summit, the shallower area going further north, and then a deeper area going further south, right? And that's part of the dynamic that's different in the Southwest Rift, and maybe why it can't feed magma from the summit down to that 1823 crack quite as easily, perhaps. Just ideas here, speculation, because we're just trying to pattern match, and that's largely what we how we try to gain insight on the volcanoes, since we don't have all the lab equipment to analyze chemistry and all the other stuff like that. So no seismic data suggests a comparable fluid core beneath the Southwest Rift. That's one big difference of the rift zones that's worth noting here. As far as patterns, number one, eruptions were immediately preceded by and may have been contemporaneous with eruptions in the summit caldera. In some instances, the level of contemporaneous lava lake in the caldera subsided as though partly drained away. So whatever's happening in this upper, shallower crack system, it's being fed by that upper lava lake and upper magma chamber directly, right? That's what we're seeing there, right? So that's tells us that it's unlikely to have a volcanic Southwest Rift Zone eruption without having a summit eruption first, right? That's an interesting thing about that dynamic there. That's a little bit similar to Mauna Loa in that sense, right? It's hard for it to just pop out there and bypass everything altogether. Number two, fissures propagated down the rift from the caldera, and the site of eruptions move continuously or sporadically down the rift in the wake of new fissures. So it propagates down here, it kind of keeps marching its way down. It always starts at the top and works downhill. That's essentially what they're saying. Number three, in the directly observed eruptions, lava was seen or heard flowing down rift in some fissures, right? So it's not pressurized in that crack where it's frothing from 3 kilometers down and it's going to fountain out of the crack. It's actually able to flow in the crack within sight from someone standing on the surface and not be fountaining out of the crack, right? So you might have gas spots in some areas. A lot of fissures certainly were putting out gas, but not enough that it's actually not fountaining out of those initial areas. It is when it's getting further down, then you start seeing the fountains and the fissures, and they build up, and you see cinder spatter cones and everything else after that. But some areas it's not doing that. That's interesting as well. This is fairly unique. And number four, lava rows erupted along many kilometers. So these are fairly long fissures that erupt in the Southwest Rift, right? That's the other part of that pattern. Some other interesting things here. The potential for eruption in the Southwest Rift may increase with the amount of seaward displacement of the south flank caused by the forceful intrusion of magma into the East Rift Zone. So let me say that again, right? As magma goes into the East Rift Zone over and over and over and over again, that torques the south flank and it may help wedge open the southwest rift a little bit so that magma can then utilize that pathway. But you can't get that unless you have a lot of movement of the south flank, in theory caused by the combination of magma intrusion and gravity as well. They only mention magma in this case. Right? They do say, this is not to suggest that dike placement is passive in the sense of magma filling a void. Right, I pointed this out as well. Here's a 71 vector diagram with arrows pointing out from the eruption site as well. Right? They say that passive emplacement will be inconsistent with the displacements during these eruptions. So that's the key there, right? And remember that we're seeing this ratio of 1 to 10 southwest rift to southeast rift, and that's kind of what they're saying as well. Is when you let's say you get to your 10th east rift eruption, maybe the next one might, maybe at that point you're more likely to have a southwest rift because you've torqued the south flank, holding it in enough, right? So we'll leave that at there. And the last thing here, which I think is interesting in our context of Mauna Loa, eruption along the southwest rift zone could be inhibited by an increase in compressive stress across the zone when magma reservoir in neighboring Mauna Loa is inflated, effectively squeezing the rift zone closed. So they had seismic crises at other times, like let's say 1975, Mauna Loa erupted in 75. Before the eruption of Mauna Loa, those seismic crises did not follow the path of 74 down the southwest rift because maybe Mauna Loa was squeezing it closed by inflating and pushing against it. So that's another dynamic that's interesting, is Mauna Loa is inflating, less likely to have a southwest rift zone eruption. And perhaps when it's not inflating, you're slightly more likely. So we'll see how, and that's another interesting thing to keep track of as these volcanoes possibly relate and possibly affect each other. And we'll watch those patterns as we progress through these next phases of eruptive history here on Hawaii Island. So this is a set of maps from Holcomb, 1987 here, that I've enlarged, and I've paired it with this table from Don Swanson's paper on a Koaʻe fault system of intrusions in the Koaʻe Fault Zone. So once again, just to point this out, our southwest rift zone is the area right over here. Our southeast rift, upper east rift is this one, and then further over this way, and the Kauai is the area in between. Right? So this is why when I talk about all these together, is because we have this era of 1964 is really fascinating, right? In the 1960s, 64, because you had magma come into the southwest rift, and then cut over into the Koaʻe Fault Zone, and then cut back up the east rift. That's pretty snake-like circuitous path for the magma to get to the upper east rift there, but that's what the pattern indicated there. So you can see that these areas are all connected. 65 to 79, you can see quite a lot of southwest rift intrusions. Here's the shallow arm, and here's the deep arm. Right, the little black spots are the lava flows during that era that were short-lived, and this larger grayer one is a long-lived eruption of Mauna Ulu that began in 69 here. And continued into the 1974 era, right through there, where you can see there's also Koaʻe intrusions. Not so much southwest rift in this era, right? Although we're definitely missing the 74 and 71 eruptions on this particular map. I'm not sure why they didn't get on here, and I did not have time to add them myself. But certainly active there. 75 to 79, you can see upper east rift, middle east rift, and Koaʻe active. And 80 to 84, quite a lot into the southwest rift, somewhat into the Koaʻe, and obviously a lot into the east rift as we fed the pool eruption. And this paper was published at that point, so there's nothing past that, but I can summarize for you guys that really from 85 to 2018, the East Rift Zone was erupting and intruding lots of times, mostly all East Rift Zone, hardly anything in the Southwest Rift, until 2006, where there was an intrusion in the Southwest Rift as well in 2006. We'll look at that here briefly as well. To understand a little bit of how this develops and how these things are all connected, we're going to talk a little bit about this Upper East Rift Zone area. Here is a cross-section from Montgomery Brown et al. Paper relating to the 2007 dykes. They're also mentioned the 97, 99 dykes, but here's our summit magma chamber. Our Upper East Rift Zone is over here. Here's the bend. Right? right? So here's where the magma is turning and then moving into the East Rift Zone and making blades that are long in this direction, right? Like the one drawn in here, right? And looking at it on an end, cut on the side, you only see a sliver of it, something like that. So it's the magma coming down, rounding this bend, and then injecting a dike, and then injecting another dike, and injecting another dike. And you maybe can see in this lower image here, 1997 is in blue, 1999 is in green, 2007 is in orange, right? And in the future, we'll talk more about this factor, right? There's a new paper that just came out about repeated periodic intrusions in this East Rift Zone area, with some period of 8 years, every 14-year periods, and combining that with the slow flip events. That's a topic for a different day. But just to show that this is an area where this does happen. Dikes get injected over and over into this area, right past the bend on the East Rift Zone, Middle East Rift here. And correspondingly, this is a measurement from 2003 to 2014. 11-year average of displacement across the East Rift. East Rift runs right through the middle here. You can see 7.8 centimeters of offset from the station north of the Rift Zone to the one south of the Rift Zone. Close to the bend and further away, you see less movement, 1.6 centimeters, but still moving, still spreading apart, right? So the Rift Zone is spreading. The thing is that on this upper side is Mauna Loa. And as the Rift Zone tries to spread, it really can't push that way at all. So when it pushes against this northern side, it ends up pushing and moving itself to the south. So the Rift Zone, in fact, this spreading across it has had a consequence, and that is this development of what I've been calling the East Rift Zone connector after Don Swanson here. And so at some early time, early in the volcano, close to when it was emerging, maybe 100,000 years ago, 150,000 years ago, 200,000 years ago, somewhere in that range, you initiate this migration, right? So at some point you had what's drawn as this connector attached to the reservoir in line with the East Rift Zone. But as the East Rift Zone erupts lava and it can't push to the north, it pushes itself to the south. Right? Then this connector has to rotate, and now it's in this position. And after another increment of time to today, now we have an East Rift Zone connector which is inclined at an opposite angle that cuts across the grain before going into what's quote-unquote the real East Rift Zone, right, where the real pathway of magma actually develops over there. So the thing is that when you have a crack that's coming this way, and then you just want to bend it over, the Earth doesn't like to crack at angles like that. You know, it wants to continue this crack across. And so across this boundary, this is the Koaʻe Fault Zone, right? At time 2, and time 3, and at time 2. And prior to that, you could have considered it being that south wall of the caldera. So it's like a south caldera wall feature migrating to the south to keep up with its East Rift Zone, which is also migrating to the south. And that's why Don Swanson proposed to call this the East Rift Connector rather than the Upper East Rift Zone, because it's a different beast altogether than what you're seeing in the rest of the Rift Zone, right? Even down to Leilani, it's different than it is in this upper portion right in here. Right? And they have various ways of trying to gauge initiation time, and so they're saying here 144,000 years, 130,000 years, 108 to 93, 81, somewhere, you know, that's the range of it, of when you started seeing the initiation of the East Rift Zone in this form. Okay, so drawn on a map here. This is a map from Don Swanson where he actually writes on here, Upper East Rift Zone, or in quotes, East Rift Connector, and that's where I've got this terminology from, even though I've messed it up sometimes and called it the Upper East Rift Connector, which kind of put them both together, and hopefully that's still clear what that means. But that's this area now that's connecting. You can see these black lines are the faults. These are the caldera faults over here, the main ones through here, but you actually have an outermost caldera fault that goes all the way back over here. It includes Puhima crater. So really, some of these eruptions that appear to be in this Upper East Rift Zone by Luamano in 74 are actually still caldera eruptions right through there. And you really have had no eruption in historic time anywhere through here, until you get to close to this bend area right through here. Hiaka, Pauahi craters, Aloi, Manaulu, Alai, all through there, right? Kind of this being the margin over here. So all through there, right? I mean, maybe you could even abbreviate it over here. No eruptions in historic time at all. At all. Right? And considering how often we've had eruptions on the rest of the East Rift Zone, that's noteworthy, and even more on the Southwest Rift than this little area right through here. But you can also see this fault system, how the East Rift Zone, I've talked about how the Rift Zone before, is really, Rift Zone is a combination of magma injecting a magma pathway and a fault zone, right? So it's a fault zone that's being used as a magma pathway, but it is still a fault zone. So here you can see that the traces of those faults and the kind of the grain of the island. And it's very easy to see this grain of the East Rift over here on the right side, moving right into the grain of the Koaʻe Fault system over here on the left side. And so it's really the same structure. And if I were to zoom out more, you'd see that this connects and aligns to the Southwest Rift further over, and we'll get to that here shortly. But first, we're going to focus on the Kauai itself, and here are eruptions adjacent to the Kauai fault system and uneruptive periods, but all of them that have shown cracks, ground breakage within the Kauai. So you can see even East Rift Zone events, 24 did erupt in the Kauai, or even down in the lower East Rift, but it cracked the Kauai. Cracked in 38 without erupting, cracked in 1950 without erupting, cracked in 1960 without erupting. 62, there was an eruption nearby, also cracked. I've highlighted those in here, the ones that erupted in this more tan color. And one eruption in purple, May of 73, we're going to hone in on, and it uses our starting case study right in here. That's the one photographed. They cut across the bottom of Hiaka Crater, the wall of Hiaka Crater, across the Chinook Craters Road, and across the roadway over here as well. So you actually can drive Chinook Craters Road, you drive right across this area. There's a little pull-off right over here now. You can walk around and see the remains of this fissure and this lava flow of May 73. It also erupted in Pauahi Crater, a little bit further to the south. But moving past these later eruptions here, what was most noteworthy is, like, here's a map of that 73 eruption, is that there was one piece of it that erupted over here on the Kauai itself. Only a kilometer in from the edge, but the first time in recorded history someone had actually seen lava come out of anywhere west of that area, right? West of that fissure. So let's zoom into this a little more. Right there it is, right there. That's this little pad. Wasn't active very long. In fact, there were reports of them seeing signs of the gases emitting and lava, and then they tried to get out there, but within an hour when they got there, they only saw gas coming out and no more lava. So it was a very, very short-lived kind of thing that occurred right over here. But that's just what made the surface, right? So there actually have been surveys done, and they did surveys in 73 across the Kauai further west, right? So it's hard to tell. This is our eruption site that we just pointed out, and here's the ones by Hiaka Crater, and further on a rift zone further over, right? So now we're talking about way further over than that. We are seeing on these profiles, I'm going to amplify this here for you guys. It looks like this. You can see like the ground is sloping down, and then there's a bulge, then a giant crack, and the bulge goes back down and it resumes. So when you see that kind of bulge, that tells you that there was lava injected underground. You can use the crack as some determination of how close to the surface it actually is, right? That's the interesting thing there. Although it gets complicated if things get loose and start falling in, that gets more complicated. In any case, during these two transects, they found evidence of magma injecting underground here and here, all this distance away from the eruption site over there. So not only is lava erupting once in a while, more often it's actually coming into the Kauai Fault Zone and injecting into these cracks passively. Now we're seeing that there's not that nearly as forceful injection, because we're not seeing a huge amount of eruption sites on this Kauai area, right? It's actually pretty rare. There was another one found we'll discuss that were found over here, these two other scoria sites we'll discuss. It was the topic of the paper by Don Swanson and all, 2018, where we got this diagram from here. So you can see from this as well that just like the East Rift can have a range, right, a whole zone, that's a width where you can have dikes come in and anywhere along it, all those cracks exist. You can have the same thing in the Kauai, where this dike is way over here, and then this one is way over here. That's a similar kind of width. So you can see that the possibility of magma coming into these cracks in the Kauai exists often. Even if they don't erupt often, they can quite often come in and fill that area underground. This is a different version of that same data, right? Where now we have drawn on here where we think that those dikes are actually in place. And this is based on this whole triangulation survey here, right? And they actually have, if you can see that, the green is where the lines ended up contracting, right? Came closer together, and the red is where they're expanding. So the dike comes in an area like this, and you see expansion from here to here. It's surrounding the dikes. That's what you see. And then everywhere else, it's getting squeezed together, right? Because of this forceful injection there and there and there, right? So interesting. It seems to have that sign of force in there as well, but it's passive enough that you don't see nearly as many eruption sites on the Kauai further up. Along those same three profiles, A, B, and C, in that previous slide, let me put it back if it wasn't clear. Here's A, here's B, and here's C. Those are the three lines across this zone. 1970 to 2018, close to. And you can see that there are certain events like earthquake swarms, or intrusions that really jump the signal up quite a lot. But apart from those step events, most of what you see is a slower, steadier rise, right? Which goes to show that this is a actively moving fault zone, and it usually moves not through big earthquakes, not through intrusions, but it kind of just creeps along and accommodates whatever's happening in the summit to the north. Remember, this is like the proto-southern caldera edge here, so it's like the accordion edge of it, and anything to the north that needs accordion south has that whole zone of deformation that it can use to accomplish that. Right? And you can do some studies of the changing rates over time and dynamics. We're not going to go to that level of depth for you guys here today, just to point out that there is that kind of pattern, and it is moving all the time, which is interesting as well. So this is not unique to 73 or other times. Here's 1965, and the darker plots on these areas are places where cracks were seen to have opened up during these surveys, and then cracks opening along the Hilina Pali Road, lots of places all through here and all through here as well, right? Showing quite a wide area of cracking during that 1965 event. Okay, let's move on from there and talk a little bit about this most recent discovery by Don Swanson and others. Yeah, and that wasn't just Don. But I'll focus on Don here. And they're marked here with these two pink dots on the Kauai over here, west of, here's our map of where the East Rift Zone was, and that eruption of May 73. And you can see a little bit better now. You can see that the East Rift connector belongs in here. The structure of the East Rift Zone is follows this way. The Kauai lines right up, and the Kauai goes as far as to where it starts curving around to feed into the Southwest Rift Zone, right? So really the Kauai is the connection, Southwest Rift to the East Rift, right? And that's why you consider this really all caldera, right? Then you can understand the dynamics a little different within this triangle than they are further in other parts of the volcano here. But focusing on these two zones right in here, this is a eruption that was just discovered recently by these researchers, and here's what it actually looks like. Here is a crack on a Koaʻe fault, and what's marked as S is this zone of spatter. Right? And it's hard to tell, it's blown up in here, what it actually looks like. Just a little layer of cinders and all that, right? It's not that unusual, especially if you've seen Leilani. But when you see it nowhere else, anywhere along a crack, except in areas like this, and here you can see it piled up, yeah, along the edge of this crack, then that gives you the evidence you need to say, oh, there's an eruption that happened here. And so they finally discovered this. They've done dating studies and chemistry studies, and long story short, it looks like it belongs in this era of the mid-1800s, right? People were around, but there was no report of this discovered yet. It can range, right, from slightly earlier to mid, but they prefer somewhere right in the middle, right in here as a possible age, somewhere 1840, there was an eruption with a lot of movement. 1868, there was an eruption. You know, somewhere maybe 1832, there was an eruption. There's that. You know, there was a whole bunch of activity through here that they could possibly correlate. Okay, let's move on from there. And show you guys this again. So what you actually can see here, this how you can have connection Southwest Rift and Kauai. And just point that out once again. Connection of the East Rift and Kauai, and you really can see those patterns now, and especially in things like this, right, where it really can see looks like the same feature across, and you'd hardly know that there was something else happening with the Upper East Rift connector right through there. Okay, so 2006 was the most recent Southwest Rift Zone intrusion. Here is an INSAR plot showing the area of the greatest deformation. And earthquakes, you see earthquakes, interestingly, the Makane Pile area as well. You see them Upper East Rift area as well. You see them in Middle East Rift Pu'o'o as well. But you also see much more of them in this seismic Southwest Rift over here, right? Not only here, but actually coming down, and it looks like it actually has a little dog leg, right? Not unlike the parallel shape of the East Rift, right? You know, a little dog leg right through there because of this whole Kauai Southwest Rift interaction right through there as well. So not as common recently, likely because you had all that open pathway to Pu'o'o, but still happening occasionally. This may correspond to that surge in magma supply we saw to Kilauea and Mauna Loa during this era, and maybe you just had too much to get it all out, and that's why you had the chance to put some in the Southwest Rift over there. And remember, you know, only 1 out of 10 erupts, so didn't erupt, just stored underground there. Okay. 2011 2012, there is a series of earthquakes. This panel here on the left, this whole one over here, the earthquake is down here next to my shoulder, and it was 2 magnitude 3.5 earthquakes. And this INSAR is suggesting a 10 centimeter drop from the line of sight look of the satellite. Fresh cracks, and when I saw, whoa, 10 centimeters drop, maybe we better go out and check that area and see that there's nothing going on there, that, you know, maybe there was a small eruption we didn't even see. They went out there and looked, no small eruption, but this is actually where they found the other one I just showed you guys, was actually right in that area. So if they hadn't seen this event and gone out there to look again, where they had actually already mapped and had already looked and missed it the first time, found it the second time, going back to look at these earthquake deformation impacts in the area. It's really fascinating. So this was 2012, 2011, similar 1.5 centimeters, magnitude 3.6, 3.5 further east, 2 centimeters of offset, not nearly as big with these other ones on the right, but it goes to show you these magnitude 3.5s are what's accommodating a lot of this motion. So when we're seeing earthquakes down in that area, that's all normal, and that's part of this, the whole caldera adjusting, right? Imagine if magma inflates the South Caldera area, it's pushing directly south on this whole Kauai zone right over there. All right, we're getting close here. I know it's been a long presentation. Thanks for bearing with me. If you guys are interested to this degree, looking at the gravity on the volcano here, we see a different pattern across the summit and the Kauai. You can see the spacing of these contours of gravity are different north of the Kauai. South, you see they're all close together, right? Close lines, right? And that is what you'd expect if you're injecting a lot of material in there, right, over time, and then sliding it away. I'm not sure exactly. Maybe I'm misspeaking here, and this is not exactly the effect. But what you're seeing suggested though is that the Kauai has the same domain, is in the same domain as the summit. So the idea being that as magma comes down Upper East Rift and injects in the Kauai, over and over and over again, you're essentially having this dike complex forming over here to the south. That's a different kind of magma storage area of the summit caldera, right, before it can get to other parts of the volcano, or in addition to getting to other parts of the volcano, where maybe you don't only activate it once you have magma going in the East Rift and coming back up, that kind of thing. So the gravity supports it as well as a point of this. So to tie it back together to the Southwest Rift here, here's our Southwest Rift zone right through here. Here's our 1974 fissures right through here. Right? And if you look closely, the traces of these correspond more closely to the Kauai direction than to the southwest rift direction. It's true that, you know, in the macro view, they do align to the direction of the southwest rift, but the individual segments align to the Kauai, right? So showing that the actual structure in here is the Kauai, even if likely that underground deep source of magma, you know, seismic southwest rift, that deeper core, is oriented more in that direction. Right? So you have an interaction of that deeper pathway and the shallower grain, so to speak. Yeah. So a different view, similar here, without as much shading, so you can really see 1974 vents, their alignment here to the Kauai, right? Even if their overall direction might be more similar to the southwest rift zone. So in comparison, here is that 73 vent on a Kauai, historic vents through here. So really, you can consider these all similar domain, especially once we saw evidence of, you know, we've seen that magma can actually go down this way and then move over here and then move back over here. Right? That's one of our more exotic examples, obviously, but it shows the connectivity that's possible through here. So, also proposed as a consequence of this east rift connector is a southwest rift connector as well. So instead of calling it the seismic southwest rift zone, an equivalent would be the southwest rift connector, because it's serving that same role where perhaps it actually had originally more of this direction, right, early on, but as the south flank, at depth especially, is moving away, it's been offset to the south. So now you have your real southwest rift at depth, your core of it, right, has the same bend right through there. But you also have a series of surface cracks shallower up because of this interaction of the volcanoes. And now you have two different pathways, a shallower one and a deeper one. And you can see how they all fit in place and connect with the southwest rift, and how once you have magma in this deep area into these cracks moving this direction, you can quite easily send it back over this way. Right? And that's how the southwest rift connects here to the Kauai, and how the Kauai connects to the east rift with the east rift connector. That's the whole story, and relevant here because of our pattern, our earthquake pattern as we see today. This is our plot today of the last month of earthquakes here, and you can see a little bit of this seismic southwest rift pattern, southwest rift connector right over here, this upper east rift zone / east rift connectors, or if you indulge me, upper east rift connector right through there, and then a whole summit region as well, right? So as we consider, if we start seeing these things pressurize and migrate more and more and more, or if we see other pathways of magma coming in, you might know what could be happening now. These are the components of this summit triangle here, which is really interesting as far as the locus of activity expected in the next phase of the volcano here. And I wanted to make sure we included earlier this deep earthquakes connection to the deep pathway of magma to Kilauea, so we know that we can ignore the blue ones as part of that deeper pathway and focus on this orange and red ones at the shallow pathway we're talking about today as the upper east rift zone, east rift connector, Koaʻe Fault Zone, and the southwest rift.